Hello everyone, my name is Mr. Ndengwa from Unlockwise. I hope I find you well. Today I'm actually presenting on the topic climatology or atmosphere and weather. This topic is part of AS level geography for those that are doing Cambridge and A level for those that are doing the SIMSEC syllabus. So today we're going to be focusing on heat budgets. That is what we're going to be looking at today. All right, so the first thing that I want us to look at is we want to define what exactly is heat budget. I want you to understand that heat budget is concerned with the movement of energy into a system, also the movement of energy out of a system, as well as transfers of energy that may occur within a system. So there are three things that are important there that I want you to take note of. Number one, we're talking about energy moving into a system. We're talking about energy being transferred out of the system, and also energy moving within the system. So we call that the energy budget or heat budget. Still there, energy budgets are actually divided into two. We have what we call macro or global energy budget. That is at a macro scale. And we also have what we call micro energy budget. That's for small areas or small places. So we can actually look at energy budgets in terms of two aspects, the macro and the micro. Macro being the global energy budget, the micro being for small places, for example, urban areas. We talk about microclimates in urban areas and rural areas. So we start energy budgets in terms of that. Okay, so I want us to first look at what happens during the day, because we have what we call a daytime energy budget. We also have what we call a nighttime energy budget. And remember, before we go anywhere, that the prime source of energy that we have in our energy budget or energy system is the sun. So the sun is exactly where we are getting our energy from. So I want to look at what happens during the day and what happens during the night. I will also teach you about the global energy budget. So with me here, I have diagrams that I've uploaded to the screen. As you can see, this one is our daytime energy budget. So it describes to us how energy flows within a system during the day. Okay, so if you're looking at this, you see that the main source of energy is incoming solar radiation, what we also call shortwave solar radiation. So this represents energy as it is being received from the sun. That is our prime source of energy. So that's shortwave solar radiation that we have here, bringing energy into the system. Okay, you are also looking at it, you see that there is also what we call reflected solar radiation. So this one represents now energy that is reflected back into the atmosphere and later into space. For example, by the ground surface itself, sometimes by vegetation, sometimes by ice or snow. I want you also to know here that the difference between incoming solar radiation and the amount that is reflected back is known as the albedo. It's known as the albedo. So we call it albedo. This is the difference between incoming solar radiation and the amount that is reflected back. In other words, it is the proportion of incoming solar radiation that is reflected back to space. So you see that here, this albedo varies from place to place. Like for example, you can see water is actually able to reflect a lot of heat back compared to land. You can even look at vegetation, also is able to actually reflect back a lot of energy. You look at ice surfaces, they're also able to reflect a lot of what? Heat back to space. So we actually say the albedo is high over water surfaces or over ice surfaces than it is for land. So we are saying that the proportion of incoming solar radiation that is reflected back to space, that we call it albedo. So we have reflected solar radiation here. It also takes place during the day. Some of the incoming solar radiation is reflected back. Apart from that, you can also see that there is also latent heat transfer. Okay, so when you talk about latent heat simply refers to the amount of heat that is needed to turn the state of a substance, okay, without changing its temperature. So during the day, there is also latent heat transfer that occurs. And in this case, I want you to know that this actually results in condensation, whereby water droplets tend to turn from a liquid into from a gas into a liquid. We call that condensation. There's also evaporation that takes place here as part of latent heat transfer. So take note, latent heat transfer is the amount of heat that is needed to take the state of a substance without changing its its temperature. Like in this case, during the day, we have condensation, whereby water vapor turns into into water droplets, and we also have evaporation as well, whereby water in its liquid state turns into gas. So this actually happens during the day as part of latent heat transfer. Still there is also sensible heat transfer. That is there. When we talk about the sensible heat transfer, we're simply talking about the movement of of heat into and out of an area. Okay, so we are saying that during the day, heat is being transferred into the area and also out of the area, for example, by winds and air masses. This is sensible heat transfer. It happens during the day. We also have long wave radiation, whereby some of the heat is lost back to space. It happens also during the day, though this one is very dominant at night. It happens also during the day. It simply describes how heat is lost back into the atmosphere and later into the upper space. So we call it long wave radiation, or terrestrial radiation. It represents how heat is lost back to space from this particular system. Also to note is this subsurface absorption. So during the day, also remember the surface has the ability to absorb some of the heat, and the heat goes into the ground. It can be stored there and released during the night. So that one is called what? It is called subsurface absorption. So this is actually what happens during the day. And if you can look at it here, we have 6 important components that make up the daytime energy budget. Okay, our incoming solar radiation, our reflected solar radiation. Take note of the albedo that I explained here. We also have latent heat transfer. We also have sensible heat transfer. We have subsurface absorption. We also have long wave solar radiation. It is very important for you to take note of that. Now at night, also we have some components that show us what happens at night. If you are looking at our diagram here that we have on this side, it shows us our nighttime energy budget. As you can see here, now we no longer have incoming solar radiation because this is at night, so we don't have the sun. Okay, so incoming solar radiation is dominant during the day. At night, we do not have here. The dominant component is long wave radiation. Okay, we have long wave radiation, where energy is lost back to space at night. This one is what actually results in the formation, for example, of dew. Okay, dew is actually formed due to cooling that results from what we call radiation loss, whereby heat is lost back to space, especially during cloudless nights. That is why if you check, when we have cloudless nights, it is very cold at such nights. Why? Because heat is lost back to space, and this is long wave radiation. It results in the formation of dew. It results in the formation of fog. There's what we call radiation fog and mist. They are actually formed because of radiation cooling that is caused by this long wave radiation or terrestrial radiation, whereby heat is lost back to space. So you need to know about this. This is a very dominant component of the nighttime energy budget. Still being there is also latent heat transfer that we also have. And if you can check here, the main latent heat transfer that takes place is condensation. That is why dew is actually found in the morning of every night. Because of what? Because of condensation at ground level. Resulting from what? Resulting from loss of heat. So the latent heat transfer that happens at night is basically condensation. Unlike here where we talked about evaporation and condensation, there it is mainly what? Condensation that results in the formation of dew, that results in the formation of fog and mist. Okay, that is our latent heat transfer. But at the same time, there's also what we call subsurface supply. That heat that was actually absorbed by the surface during the day, right? It is released back to the surface at night. So that becomes our source of heat. Since we don't have the sun, here with the nighttime model, the heat is coming from the what? It is coming from the ground through what we call subsurface supply. And also to note is our sensible heat transfer, right? Heat is always moving into the area and out of the area at night, just like it is happening during the day. So that gives us our nighttime energy budget. It's different from the daytime energy budget in the way I've explained it. I think it's clear. So what is important now for examination purposes is you need to understand these components, be able to describe them, be able to explain how they take place. Sometimes we can just say, define the term sensible heat transfer. You should be able to do that, to define, isn't it? Sometimes they just say, what do you understand by latent heat transfer? You should be able to also know that. So it's very important to know the components of each of these modules. It's very important to do that. Now I'd like us to move and look at what we call the global energy budget. Okay, so if you actually remember very well, you understand that the sun actually gives us 100% insolation or heat. But a lot of things actually happen during the the process. We don't receive 100% of the heat or insolation. Otherwise, if that would happen, there will be no life on Earth. So you're going to understand that there is, for example, reflection that happens, whereby some of the heat is reflected back to space. For example, by clouds. Clouds have the ability to reflect heat back to space. Also, you can see how some of the heat is absorbed by the atmosphere when it reaches us. So the atmosphere has the ability to absorb some of the heat before it reaches the Earth's surface. There is also what we call scattering that happens, whereby some of the heat is transferred by gases and dust particles, right, before reaching the Earth's surface. Vegetation reflects, okay, until from the 100%, only around 24% actually reaches the Earth's surface. You have to check on that. You actually find the global energy budget diagram. It actually shows us exactly what happens with 100% insolation that we actually receive until we only have a smaller proportion of that particular heat that is released by the sun reaching the Earth's surface because of processes like reflection that I've explained, absorption that I've explained, scattering that I've explained, that actually distribute and move the heat so that only a small proportion reaches here. It is very important for you to take note of that. But my major concern is about what we call the heat balance. It's about what we call the heat balance. So I want you to know that there is a very important aspect called the heat balance. Okay, I will explain it in a very interesting way. Just going to do this. This is my 0 degrees, that's the equator here, and I'm going to put 90 degrees there, north. This is my 90 degrees south. Then I'll put 60 degrees here, and I'll put 30 degrees there. So here I also have 30 degrees, 60 degrees, and this is south, this is the north. And this is our sun. Right. So if you check here, you see that the sun is directly overhead at the equator and in the tropics. And because of that, you understand that the equator and the tropics, they receive a lot of insolation compared to any other parts of the world. If you're going to look at the poles, you're going to see that the poles, they actually receive the sun at an angle. And if you look at it, the sun's rays, you have to travel longer to get to the poles. And that is why the poles are cooler. And if you're going to check now, you see something interesting there. That the tropics and the equator are actually not being overwarmed. Neither are the poles being over what? Cooled. Why? Because there is what we call the transfer of heat. That occurs whereby heat is being transferred from places where there is a surplus, areas where there is a deficit. Where do we have a surplus? We have a surplus at the equator and the tropics here. We have a surplus. Why? Because here the sun is directly overhead. And the sun's rays actually travel a shorter distance to get to the what? To the Earth's surface. So because of this surplus, heat has to be transferred to go where there is a what? There is a deficit. I will explain how this actually what? Take place. So we call that horizontal heat transfers, whereby they are actually trying to transfer heat from the equator and the tropics to the poles. For example, by very high winds, like for example jet stream that can actually travel at speeds ranging around 180 kilometers per hour to displace the heat from where there is a surplus to where there is what? A shortage. For example, here, if you're going to look at what we have here, you're going to see that from this particular what? Graph that you see here, right? You can see that here, that's where we have our equator, the 0 degrees latitude, right? And here we have our poles there, right? Here in the tropic, that's where we have a surplus of heat. Why? Because incoming solar radiation is greater than what? Heat that is being lost. So because of that, we have what we call a what? A positive what? A positive heat balance. Why? Because we are receiving more insolation than what we are losing. So there is a surplus here. And in the poles, you can see the poles here. They have a deficit. Why? Because they are losing more heat than they are receiving. So there is a deficit of heat. And you can see that there are heat transfers that are taking place, whereby heat is being transferred from the equator and the tropics to go to the what? Go to the poles. Right. Now, how is this particular heat transferred? So, like what I was saying, here we have things like, for example, high winds. So, high winds, they play a very important role in transferring what? Heat from the tropics and the equator to the poles. These are very fast-moving winds. A very good example is the jet streams that I said that they take about only 2 weeks to revolve around the Earth, moving it around 180 kilometers per hour. So they can take energy from here and distribute it to the what? To the poles. Apart from that, we also have pressure systems. Okay? Pressure systems like what? We're talking about things like depressions, hurricanes. They move from the tropics, also dispersing heat to places where there is a what? There's a deficit. You need to know that. We also have ocean currents. Okay? Ocean currents also convey heat from where there is a surplus, which is the tropics and the equator, to the what? To the poles. So it's very important for you to know that ocean currents also play a very important what? Role. Also, we have deep sea currents. They also play a very important role in distributing what? Heat from here to the poles. This is a very examinable area. You need to know. Sometimes they just bring you this thing and they want to explain. They want you to describe and explain what is happening there. So like what I'm saying, we have a surplus of heat there. Why? Because we are receiving more insolation than we are losing. So we have a surplus, right? And here we have a deficit. Why? Because we are losing more insolation than we are. And I've explained that using the diagram that I put on the diagram before, on the board before. So we have a deficit there, right? So to actually avoid overheating there or overcooling there, there's transfer of heat horizontally that happens. So that results in us being able to achieve a heat balance. So this is horizontal heat transfer that I'm talking about here. But there's also another interesting issue that I want to explain about, which is called vertical heat transfer. So, if you didn't know, the sun's rays are only converted into heat upon reaching the Earth's surface. So this is our Earth's surface, and we have the sun there. The rays are only converted upon reaching the what? Earth's surface. But if you check now, the Earth's surface is neither being overheated, neither are we having the upper atmosphere being what? Overcooled. If you're actually following, I actually said the rays are only converted into heat upon reaching the Earth's surface, and we are not actually having overheating here, neither are we having overcooling here. Why? Because of what we call vertical heat transfers. So how exactly does this take place? This takes place in this scenario. Like for example, if you're looking at here, we have heat here. The heat has to be transferred back, for example, by processes like conduction. There is convection, there is radiation. So these ones are the three processes by which heat is transferred vertically to avoid overheating on the Earth's surface and overcooling in the upper atmosphere. When we talk about radiation, radiation actually occurs when heat is lost back to space, especially during cloudless nights. Okay, I've explained about radiation, and it results in what we call radiation cooling, which can actually form radiation foam, which can form also dew, right? So you need to know about this one. Then there's also convection. Convection, you know this one. Each time a pass of air is heated, it becomes light and unstable. So it rises. So in other words, what we are having here is we have a pass of air being heated, it becomes unstable. So it rises, and then it cools up there, which means that heat is being transferred up from the lower atmosphere because of air masses becoming unstable. Each time a pass of air becomes unstable, what happens to it? It rises. So convection makes sure that when the air cools now there, it descends back because it becomes denser. So it comes back to replace the warm what? The warm air. So here we are actually having a pass of air that is warm, rising to warm the upper atmosphere, and a cooler air mass descending to what? To replace the what? The warm air. So we are going to have a balance of heat, whereby the lower atmosphere is not being overheated, neither are we having the upper atmosphere being overcooled. That is vertical heat transfer. Also, there's conduction, whereby heat is transferred through particles like dust and other gaseous particles, isn't it, from the lower atmosphere to the upper atmosphere. So heat transfers are in two types. The horizontal heat transfer, whereby heat is being transferred from the tropics and the equator to the poles, right? Then there's vertical heat transfer, whereby the heat is being transferred from the lower atmosphere, where the heat is being formed, to the upper what? Atmosphere through conduction, convection, and radiation. So it's very important for you to what? To take note of. Okay, so I also want us to look at global factors affecting insolation. Remember, the term insolation in this case simply refers to what? To heat. So there are several factors that affect insolation, which is heat from the sun. And this actually causes global variation in our temperatures. Okay, I'll just browse through those ones. Okay, so you're going to look at things like latitude, right? Latitude is simply distance from the equator. Okay, you're going to see that, like what I've explained just before, areas that are right by the equator and in the tropics, they actually receive a lot of insolation. Why? Because the sun is actually reaching those particular places at right angles. So they receive more insolation, and because of that, they have a higher temperature than high latitude areas. So you can actually recall from the diagram that I first drew when I was actually saying that the sun is overhead at the equator. That is what is about latitude. So you see that high latitude areas, they receive insolation at an angle, so they have lower temperature than what? The equator in the tropics. Then there's also altitude. So here, altitude is about what? Height above sea level. Generally, you know that in the troposphere, this is for geography people, right? In the troposphere, temperatures decrease with what? With height, isn't it? What we call the environmental lapse rate. So we expect that the higher you go, the cooler it becomes in the troposphere. You know what happens in the stratosphere and other layers, you know about that. So altitude also influences your temperature or insolation. Then apart from that, we also have things like ocean currents. Ocean currents have a tendency of altering the temperature of places where they blow towards. Okay? Like for example, if you have a cold oceanic current, like for example here we have the Benguela current that comes from the Indian Ocean. It's a very cold air current. If it blows towards a particular area, it reduces the temperature of that particular place. So ocean currents have a tendency of influencing temperature conditions of places to which they blow. If it's a cold ocean current, it brings lower temperatures. If it's a warm ocean current, it brings warmer temperatures. The same with prevailing winds. So prevailing winds also have an influence on temperature. Why? Because wind also has the ability to carry heat. So if a warm wind blows towards a particular area, it also brings warmer conditions. It's very important for you to know about that. You can even also look at land and sea. This is also a very examinable area, land and sea. Right here, you have to know something here. The land and the sea, they have what we call different specific heat capacities. Okay? We're talking about the amount of heat that is needed to change the temperature of a 1 kg pass of air by 1 degrees Celsius. So if you're going to look at it here, land requires less heat to actually raise its temperature than the sea. The sea is so transparent that it allows heat to penetrate. So you need more heat to raise the temperature of the sea than you need for the on the land. So in other words, we say that the sea has a higher specific heat capacity than the than the land. That is why now you see that if we are in winter, right, the land is much cooler. Although it is very quick to absorb heat, it is also very quick to lose heat, right? So you see that in winter, land areas are much cooler than the sea. The sea is much warmer in winter. Though it is slow to absorb heat, it is also slow to lose the heat. So in other words, seas and oceans, they act as what we call thermal stores. They can store heat. I hope you are seeing that. You can even see this. If you try and swim at night, you see that sometimes it's warmer in the water if it's in winter than it will be on land. Why? Because water has the ability to retain heat. So you need to understand how the land and the sea have the ability also to alter temperature conditions, referring to the winter and the summer, isn't it? In summer it's vice versa. The land is much warmer than the sea. So it's very important for you to know about this. It's very important. Then apart from that, there are also other factors that are there that we call short-term factors that affect also insolation. Like for example, you can talk about seasons. Yeah, normally seasons are affected by the angle of the sun. Because remember, the sun also, there are times when the sun is overhead, right? And there are times when the sun is away from us. But the sun moves, okay? It's always around the equator most of the time, but it moves north and south. Normally when it moves north, it means those that are in the south, they are getting into winter. If it moves south, it means those that are in the north, they are getting into their winter. That is what causes seasons. So seasons actually affect in a very great way our insolation or temperature conditions. Apart from that, you can also talk about things like length of day and night, right? So the longer the day is, the more insolation we're going to receive. So we have longer days and shorter nights. We have more insolation in the higher temperatures than when we have shorter days and longer what? And longer nights. It's very important for you to what? Know that. There are also other local factors that you can also consider, like what we call aspect. Aspect is a local factor that influences what? Insolation. Which direction are the slopes facing in relation to the sun? So you say that north-facing slopes in the northern hemisphere are always in shadow. So they actually receive lower what? Lower temperatures. So aspect is a very important what? Factor that affects insolation. Even cloud cover. When you talk about cloud cover, you're talking about the thickness of the cloud cover or the type of cloud cover. Because remember, I said clouds have the ability to absorb and even reflect heat. So it's that normally when we are having a cloudy day, a lot of heat is absorbed or reflected back. This leads to lower temperatures in the what? In the atmosphere. So it's a very important factor that you also have to what? To consider, which is cloud cover. So there are so many other factors, like for example, if you talk about urbanization, I will explain to you one day about what we call microclimates, where I'll be talking about urbanization, how also urbanization can alter climatic conditions. Okay? Because why? If you look at urbanized areas, they have a lot of gases that are in the atmosphere that have the ability to absorb what? Heat and increase temperatures, resulting in what we call urban heat islands. So I'll explain also about that. So for today, I want you to understand the energy budget, the global, understand what happens during the day, the daytime energy budget, nighttime energy budget, the transfers of heat that I taught you about, which are the horizontal heat transfers and the vertical heat transfers. We need to understand those ones, and also the factors influencing insolation. So this is for today. See you next time. Please keep following us, subscribe, share, and make sure that you are part of the team and likewise. Thank you.